Okay. So we got acids and bases to work with today. So we'll do the last chapter on just general chemistry. And next week we start into organic chemistry. So we'll talk about acids and bases today. And again, more definitions, just like there's definitions with unit 4 and 5, more definitions, concepts in this unit here, acids and bases, along with some other calculations to kind of build on what we've been doing in the previous two units here. So here we have Svante Arrhenius, right? And he helped us define, provide some definitions into how to identify an acid or base, right? So we have some substances that are acidic, some substances that are basic. They'll range on a pH scale, if you've ever heard of that, and we'll get into the pH scale later today. But we first have our definition by Arrhenius that acids will produce hydrogen when they ionize. All right. So, very simple process on how we ionize acids, right? We just simply put it in water. We put it in water. We kind of went over part of this yesterday, or I'm sorry, on Tuesday, when we were talking about ionic compounds, where you just put them in water and then they ionize. We get ions. And the same process here for producing acids. When we put, this is hydrochloric acid here with gas form, we put it in water and it ionizes, and we can see that it produces these hydrogen protons. All right? So when we see H plus, you may hear me refer to it as a hydrogen proton. Right? And that's simply what it is. If we have hydrogen here, hydrogen has one proton. It also has one electron. But if we remove this, we simply just have one hydrogen proton, right? There's no neutrons with most of hydrogen anyway. So when I say hydrogen proton, I'm talking about just a hydrogen atom there that doesn't have an electron. So this will, when ionized, we just simply put it in water, and it produces hydrogen protons. Right? So we can identify this as being an acid. So any acid, when we ionize it, will do that. So if I put hydrobromic acid, so this is HBr, hydrobromic acid, and we simply add it into some water, is we're going to get H plus some Br minus. So as long as we produce hydrogen protons, is that this could be considered an acid. So let's put this into water. If I put this into water and I ionize it, I'm going to get lithium plus I'm going to get hydroxide. So did we produce hydrogen protons? No. So could we consider this to be an acid? No. Simply because by Arrhenius' definition is that since we did produce hydrogen protons when we ionize it, that this would not be considered an acid. So our acids can also be identified in another way. Is that most acids here, you're going to see this hydrogen out front. Right? So we see a hydrogen out front like that. We can also assume that that's going to be an acid. So here's another acid here. So one way I could try and identify it is I see this hydrogen out front. And if I ionize it, that hydrogen out front is likely to produce a hydrogen proton. So here, because we produced this acid, is that this, or produced this hydrogen proton, is that this must be an acid. So we also had a definition for bases. And if we put a base and ionize this base, right, we put it in water, is that it dissociates and we produce hydroxide ions. So if we produce these hydroxide ions in this process, is that that's going to produce a base. So we know that this isn't an acid, but we did produce hydroxide ions here. So could we consider this to be a base then? Yeah, absolutely, because we produced these hydroxide ions. So the two definitions we have there then by Arrhenius. So there are other definitions. The first definition we're just learning today is just going to be Arrhenius acids and Arrhenius bases, right? On how to identify them. Now, some properties of acids and bases. Right? Acids conduct electricity. Bases also conduct electricity. The reason they can conduct electricity is, well, we're producing ions, right? These aren't covalent. This isn't a covalent compound here, it's an ionic compound. And even though these are covalent here, is that when they dissociate, when we ionize these, is I don't get a partial charge, right? Is I get this full positive negative charge, and those positive negative charges can conduct electricity. Acids are sour tasting, right? Limes, lemons, we know what a sour taste is. So acids will taste sour. Bases will taste bitter. I don't know if you're familiar with a bitter taste. If you've ever accidentally maybe got shampoo, like conditioner, like, you know, on your lip or something like that, that's what we consider a bitter taste, right? Soap, those are bitter tastes. Those are all types of cleaners, are all types of bases. Number 3 is a concept that we kind of need to keep in the back of our mind as we go through this chapter. Right? Is that acids will neutralize bases and bases will neutralize acids. So if I spill some acid on the table, if I wanted to neutralize that, I would put some base on there and neutralize it. If I spilled a base on the counter, I would get some acid and put it on there and I would neutralize that base, right? So acids neutralize bases, bases neutralize acids. Acids react with metals to liberate hydrogen gas. So let's kind of talk about this one here, right? Just so we get a clear understanding of that particular statement. Right? We had an experiment in lab 4. So in lab 4, we took a piece of mossy zinc. We took a piece of mossy zinc and we added hydrochloric acid to that. And what we produced is this started to dissolve, right? It became aqueous and we got some zinc chloride. Plus, we saw some bubbling and we got some hydrogen gas, right? This is the one where we took a splint and we made water, we get that reaction there. So when we put metals, right, when we put acid and metals together, is they liberate hydrogen gas, which is just another way of saying that it produces hydrogen gas. Right? So I could replace this with another type of metal. If I add acid to it, we're going to produce hydrogen gas. Bases feel slippery on the skin. So like I was saying, like shampoos, oven cleaners, like those type of things, is that we're going to see. You don't have to memorize this list. These are just kind of examples just to kind of get some thoughts here, right? So, right, sodium hydroxide, drain cleaner. These are kind of slippery, you know, antacids. Now, different types, right? Sulfuric acid, that's what we have in our car batteries. Carbonic acid, that's what, you know, gets your Coke, Pepsi, whatever, Red Bull you're drinking. You know, that's the bubbles that we get in there. But different types of acids, different types of bases. But let's look at some similarities between these acids and bases. Right? Is that I mentioned this before, and we kind of notice here, like all of our acids have at least one hydrogen out front. Some have more. All right. Some have more, some have just one. Maybe if they have two, could have three. But we always see that there's a hydrogen out front. And for the most, for the most part, with the exception of ammonia, and we'll talk about that one once we get to another definition here. But other than that, we also see a similarity with all our bases, right? Is that they do have hydroxide in there. If we're using Arrhenius' definition, if I were to put this in water, we're going to get potassium ions and hydroxide ions. We're going to get calcium ions plus some hydroxide ions. Okay, magnesium ions plus some hydroxide ions. And as long as they're producing those hydroxide ions, we're going to know that those are bases. And this one, we can't really tell if it's going to produce a hydroxide ion. So we are going to learn another definition that will give us some insight as to why this one is considered a base. So we're going to learn how to name bases. Bases and some acids. So first we're going to learn these acids. These are what we call binary acids. So this HCl is a binary acid. And when we look at the word binary, right? Binary, right? That prefix should make us think of the number 2, which means that here I simply just have two elements, one of them being hydrogen and then another element, right? So just two elements. These are what we call binary acids. So our binary acids will only contain hydrogen and one other element. So for all binary acids, they will begin with this prefix hydro. And I've already talked about the HCl, hydrochloric acid. Right? So they're all going to begin with hydro, and they're going to all end in ic acid, hydrochloric acid, hydrosulfuric acid. So they all begin with hydro and they end with ic acid. Right. This is not dihydrogen sulfuric acid, right? We just begin with hydro. Whether it has one hydrogen, three hydrogens, it's just beginning with hydro. Not trihydro, not dihydro, not tetrahydro. We just begin with hydro regardless of how many hydrogens are there. I would absolutely do something similar to this on the exam. We have to know how to name acids, right? Nomenclature is part of what we do here as chemists, right? Dihydrogen, well, I already know that the answer is not di. We don't put di when we're talking about acids. We use di when we're talking about covalently bonded molecules, right? Here, hydrosulfuric acid, this is obviously the right answer here. Would I put dihydrogen sulfide when I'm asking you to name an acid? Yeah, I absolutely would. Dihydrogen 2-sulfuric acid. Why am I not using this 2 here? Because it's not a transition element, right? There's no reason to have it something like that. So we do need to know these rules, right? There's a lot of rules to naming, and we have to know these rules here. So let's move on with some different, let's put some different acids here. Knowing that they're all ic acid, right? I'm gonna just kind of help name all of those. Let's start with all right. It's going to begin with what? Hydro. And we're not doing, we kind of cut the name. So we're not going to put nitrogenic acid, we would just use nitric. So hydro, nitric acid. We already have hydrosulfuric acid, hydrochloric acid. How about this one here? So this one here would be hydro. This is phosphorus, but we're going to cut that down. Hydrophosphoric acid. We have HBr, HF, HI. So this would be hydrobromic acid, hydrofluoric, U before O, hydroiodic, so we have all of these different types of acids here. I think that's I think we got all of them there. So these would be all of your binary acids, right? Hydronitric, hydrophosphoric, hydrobromic, hydrofluoric, hydroiodic, hydrochloric, and hydrosulfuric acid. These are all what we consider to be binary acids. Even though there's a 3 here, right? This is still a binary acid because it contains 2 elements. Right? I didn't say that it contains 2 atoms, but it does contain 2 elements, hydrogen and phosphorus, hydrogen and nitrogen, hydrogen and sulfur, even though there's multiple atoms of hydrogen in there. Then we get to oxy acids. So this is a different type of acid. Oxy acids contain oxygen. So anytime we see oxygen, that's how we're going to identify those as an oxy acid. And we use polyatomics, right? If you haven't memorized your polyatomics, good luck on the exam, right? Because I had you memorize them. I put a lot of weight on the exam, learning them because they're just not going to go away, right? We need them for organic chemistry. We need them for biochemistry. You need to know your polyatomics, right? Without knowing your polyatomics, I can't identify if a compound or substance is going to be soluble or insoluble, because we have to know nitrates, acetates, phosphates, right? Hydroxides, sulfates, carbonates. We have to identify them in order to determine whether it's going to be soluble or insoluble. If we don't know them, we're not going to be able to name these bases. Thank you for pointing that out. NO3. NO2. All right, so this here is nitric acid. And our polyatomic here is nitrate. Right? So nitrate will end in ic acid. While nitrite, this is nitrous acid, and this is nitrite. Anything that ends in ITE will be OUS acid. Right. And again, we have plenty of examples. Phosphoric acid, phosphorus acid. Sulfuric acid, sulfurous acid. We have carbonic acid. Carbonate, permanganate, acetate. But there's plenty of polyatomics that have either ITE or ATE. And if we don't memorize those polyatomics, we're not going to be able to identify these particular acids. So if we start with this first one over here, and again, oxyacids do not use the hydro prefix. Right? Oxyacids do not use the hydro prefix. So we have H2SO3. So does anybody recognize this polyatomic? What? Sulfite. This is sulfite, which means this is going to be called, we're not going to begin it with hydro because it's an oxyacid. So this is sulfurous acid. Sulfurous acid. HBr, is that a binary acid or an oxyacid? Binary acid. Right? There's no oxygen there. So this would begin with hydro. So hydrobromic acid. HClO4. And if you're lost on these, I believe the page is 3-5 in your textbook. So you can flip over there. I believe it's 3-5. Let me look. 3-5, yes. So HClO4. Well, there's an O here, so I know this is an oxyacid. So what is the name of this particular polyatomic?
Perchlor?
So this is perchlorate. So this is perchlorate. So because it's ATE, this is going to end in ic acid. So this is then perchloric acid. Perchloric acid. H2S, it's a binary acid. Let's begin with hydro, hydrosulfuric acid. Then we have HClO. Another polyatomic. This is an oxyacid. So what is the name of this particular polyatomic? This is hypo, not hydro, hypochlorite. Ends in ITE, so this is going to end with OUS acid. And we have hypo, and I'm going to leave the hypo there because again, it's the hydro that we don't use here. But hypo is part of the polyatomic name here. So hypochlorous acid. H2SO4. So H2SO4 is sulfate. So we would not put, we would change this to ic acid. So the last one being sulfuric acid. Right? But there's plenty of examples, and any of them can be pulled from there. One more that we just kind of commonly use. This is one that we use kind of just most of the semester. We kind of use a lot of this actually. I believe we're going to be using it in today's lab. Is this here? Right? We know it's an oxyacid simply because there's oxygen here. But what is this polyatomic here?
Acetate.
So this is acetate. Ends in ATE. So this then becomes, I'm going to drop the ATE and add ic acid. and this becomes acetic acid. And acetic acid, we use plenty of it throughout the semester here, so just to get a little bit of understanding with that there. All right, so I did mention the pH scale earlier. So this is our pH scale. pH stands for the potential of hydrogen, right? How much potential does that hydrogen have? Right. So it can range anywhere from 0 to 14. This is where we view our pH scale. And 7 just kind of being right in the middle. And 7 is the pH of pure water, right? Not water from the tap, right? But pure water. Anything less than 7 is considered to be acidic. Anything higher than 7 is considered to be basic. But then there's kind of ranges of acidity and basicity, right? There's ranges. Something can be kind of acidic, right? Lemon is kind of acidic, right? Orange juice is a little bit acidic. Hydrochloric acid, well, that's very acidic, right? Here, eggs. Eggs are slightly basic, but sodium hydroxide is very basic, right? So there are ranges of how strong or weak an acid is. There's ranges of how strong or weak a base is. Now, in pure water, this is shorthand that I use, or that we use, chemists use, right? If we see brackets like this, is that we're talking about acids, bases. This will translate into the word concentration. Right? So if I do this, does everybody remember what I call this here? Hydrogen protons. So if I put this here, what does this translate to? Concentration of what? Of hydrogen protons, right? So concentration of hydrogen protons, right? If I put this, right? Concentration of our hydroxide ions. But a little further than that is Arrhenius had a definition for us, right? If we produce hydrogen protons, what did we consider those to be? In a reaction, if we produce hydrogen protons, those are acids. So this represents an acid, while this represents a base. So we could say this is the concentration of hydrogen protons, but we could also identify it as the concentration of acid. Concentration of base, right? So if I say the concentration of acid, this is what I'm talking about. Concentration of base, this is what I'm talking about. Concentration of hydrogen protons, concentration of hydroxide ions, concentration of acid base, this is what we're referring to. So in pure water, the concentration, we know that capital M to be molarity, right, our concentration. So in pure water, the concentration of base is 1.0 times 10 to the minus 7 molar, and it happens to be the same for the concentration of base, those hydroxide molecules there. So in pure water, because water is neutral, it would make sense that we have equal amounts of acid-base ions, hydrogen proton, hydroxide ions there. We have an equal amount, and we can see that water is simply neutral. Right? We might see this term here. When we're talking about acids and bases, those are interchangeable when we're talking about acids and bases. So this is interchangeable with this. All right? So these two represent the same thing. Before we go any further, we just kind of want to explain how we get, or actually no, we're not at that part yet. We need another definition in order to look at that there. Yeah, we need another definition. Just for right now, understand that if you see this, we're still talking about the concentration of acid, right? This is our concentration of hydrogen protons. We could say this is the concentration of acid, and since these two are interchangeable when we're talking about acids and bases, this also represents the concentration of acid. Okay? So we see here the concentration of acid and base is the same. Now, if I want something to be more acidic, well, I need the concentration of acid to be higher than the concentration of base. So I need more acid if I want something to be acidic. If I want something to be more basic, well, I need more base, and then it becomes more basic. So when looking at these, we see these numbers here, minus 14, this is minus 1. The pH of water is 7, and here it is 10 to the minus 7. That kind of plays a little part when we're looking at pH values, those number values. If I want the concentration of acid to be higher, on this number scale, 10 to the minus 1 is much larger than 10 to the minus 14. Okay? So if I want something more acidic or more basic, just so that we understand the next image here. And these aren't in your textbook, unfortunately, so I have these here. But here, if I want something more acidic, well, we need to add more acid to it. More acid, less base. Right? More base, less acid. So we're going to learn this definition here and how we get this value here. So this is a constant. This number doesn't change. This is a constant at 25 degrees Celsius, 1 atmosphere, is that the Kw, our dissociation constant for water, is 1.0 times 10 to the minus 14. This comes from taking the concentration of acid and multiplying it by the concentration of base. If I take this and multiply them together, I get this value. So if I take 1.0 times 10 to the minus 7, and I multiply that by 1.0 times 10 to the minus 7, I'm going to get 1.0 times 10 to the minus 14. All right? So anytime we multiply these two together, this is what the answer is. This is also why we see this tilting scale here. If I add more acid, there has to be less base. Not the same amount of base, there has to be less base. If I add more base, then there has to be less acid. Because this value will always calculate to be 1.0 times 10 to the minus 14. Okay? So if I increase this acid, then this value has to go down. If I increase the base, then the acid value has to go down. So here we're going to actually start to calculate, and I'm going to leave this information here. Yeah, I'll probably work on some stuff over there. So to get the pH of water, this is our formula for pH. That pH is equal to the negative log of the concentration of acid. So the negative log of the concentration of acid, and I'm going to actually write both of these here just so we're not confused here. It is the exact same negative log of the concentration. I'm going to put H3O plus, right? Because these are interchangeable, right? We've already agreed that these two are interchangeable. It's pH, the negative log of these acids. Now, let's make some calculation here. Actually, you know what? No, let's calculate water real quick. If we know these values for water, in pure water, the concentration of acid, these hydrogen protons, is equal to 1.0 times 10 to the minus 7. So I want you to take your calculators out. If you don't have your calculator, I can't help you. All right? Find the log button. Okay? Find the log button. I'm going to help everybody understand their calculator. Different calculators calculate it different ways. See Azalea here. Let's take a look at. So yes, we have. Let's see if there's another one there that we can use. Yes, this button. So don't use this one. You're going to use this one. So see how this is gold? You're going to hit. So let's clear this out. You're going to hit this button and then then this button here. Right? So there we go. So it doesn't have that thing down. But before that, we need to hit negative. Right, and don't hit the subtract sign. Subtract is not the negative, right? We're going to hit negative. So if you put this into the calculator, pH is equal to the negative log of 1.0 times 10 to the minus 7 . Your calculator should say 7. Right? Your calculator, I think, Andrew, you got the same one over there? Yeah. Don't use, okay, yeah, you use this one. Okay, perfect, yeah. What was that? You got 6. Let's take a look at your calculator.
Is there significant figures in here?
Yes, there are significant figures that we have to deal with. All right. So we need to do scientific notation. So don't put the times 10. You're just going to put 1.0, then use that double E button. The double E represents the times 10. And then, but we need to put negative first, so negative log. Are we getting it? Negative log, and then you're going to hit the 1.0. This is your scientific notation button, and then you'll hit negative 7. And then just, hit equals, and then you get 7. Yes, like that, right? Right, where's your negative button? So let's find your negative button first. So let's hear, we're going to find, so hit negative first, so negative. This is your log button, and then you're going to put 1.0, and then let's hit this button here. I think this is your, yeah, let's hit that one there. Yes. So this is your scientific notation button, and then you're just going to put in negative 7. That's subtraction. This is negative. Negative 7, and then hit enter. And then we get our answer of 7. Yes. There was a different calculator. Yes. You have to do yours in reverse. So what you're going to do is you're going to start with the coefficient 1.0, and then you're going to hit the double E button, -7, and then you're going to hit log, and then you're going to hit negative. Right, so this is the same, yeah, so you're just doing it in reverse just because the calculator, so you'll put the coefficient in, then hit log, and then hit negative, instead of negative log and then the number, right? Anybody else? We're good? Over here, Victor?
I did have a question. It's the double E button.
Yours is right here.
Yeah.
So that's the same as the double E button.
Okay.
Yep. All right. Your calculator gave you this answer. This is the correct answer. The rule for this, and I even put it in red here so that nobody forgets, the number of significant figures in the concentration of acid, however many, the number of digits after the decimal places, so here maybe this is 7 point, the number of digits after decimal places in the pH, the number of digits. So here, how many significant figures do you see here? 2. So I need to be 2 digits after the decimal, because this is 2 significant figures, right? So how many significant figures are in our acid concentration? That's how many after the decimal place that we need to be. So if this was the concentration, 1.00 times 10 to the minus 7, then we would be 7.000. 3 significant figures, 3 after the decimal for our answer. Right, Hannah? I'm going to have you help me with the next one. I'll have you help me with the next one. Yes, yes, of course. All right, so we're going to do lemon juice. There's the concentration of our acid. So concentration of our acid is 1.1 times 10 to the minus 2. So we're going to go pH is equal to 1.1 times 10 to the minus 2. Oh, let me write that out in an actual problem. Negative log of 1.1 times 10 to the minus 2. And we're going to wait for Hannah to give us that answer, because she's going to help me out with significant figures. You can do it. You can do it. No, I'm right here. I'll walk you through it. All right, so let's find the negative. And let me calculate this along with everybody. Let me get a calculator out. All right, so we have the negative. Negative log. All right, so out to, let's go out to 5 digits first. So what's the answer going out 5 digits on your calculator?
1.9586.
All right. If this is the concentration of acid, how many significant figures do you see there? 2. So that means we need to be 2 after this decimal place. So we would round this to then 1.96. So our answer is 1.96 pH. Thank you for the assistance, Anna. All right. It's by pure coincidence that I happen to know the pH of dark Modelo. Purely coincidental. This is the base concentration. And I'm going to ask a few questions before we attempt to solve this. So, the base concentration is equal to 4.0 times 10 to the minus 10. Can we use this formula here? Can we use this formula here? No. Because this is what I have. This only works with the concentration of acid. This only works with the concentration of acid. But do we know what this value is? Here's 1.0 times 10 to the minus 14. And we know what this value is. It's 4.0 times 10 to the minus 12. So when you're given the base concentration, we need to work at getting this. So we're just going to rearrange this real quick, right? If I divide both sides by this base concentration, this is just a little bit of algebra work. This cancels out this, and we get this Kw over the base concentration is equal to either one, because again these are interchangeable. So if I want this concentration, I have to do a little math work first. We know that value up there, that's 1.0 times 10 to the minus 14 divided by 4.0 times 10 to the minus 10. And this is equal to this concentration. So let's all calculate this out. 1 point so clear, 1.0 times 10 to the negative 14 you're going to get one of two answers here, or you should anyway, right? I got 2.5 times 10 to the minus 5, or you're going to get 0.00025. Excuse me. Yes. All done? All right. Thank you so much. If you got this answer here, which is incorrect? If you got 2.5 times 10 to the minus 25, I need to know, because I need to help you with your calculator. So this calculator is not user-friendly when it comes to scientific notation. So you're going to do one of two things here. And let me double check that here. So 1.0 is this. Negative, where's the negative? What would I call negative? Is that, oh, oh, here. Oh, there it is. It's right above it. So not user-friendly when it comes to scientific notation. So 2 things you can do here. If you're dividing it, you can use this and then do one on top of the other. Or you need to put each set of whatever you're doing in scientific notation has to be in parentheses. So it doesn't matter to me which one you do, but try that and let me know if that fixes the issue. Does anybody else get to the minus 25? No, everybody else is good? All right. So now that we have this answer here, this is our concentration of H+. So now we can use this formula here, and we can say that the pH is equal to the negative log of 0.00025. 2 significant figures. My answer should be 2 past the decimal place. So negative log of 0.00025.
Why don't you just give me a fraction?
Oh, it did give you a fraction. Let's see if we can convert that. Do you have anything that would convert it? All right, so you're going to hit that format button, move it over to decimal, and then hit enter. And there's 2.5 times 10 to the minus 5, which is our result. So we're good. All right? Okay. So now, Azalea, let's have you calculate this out. So now put this into your calculator, negative log.
4.60.
Okay, yep, I'll take that. So we have 4.60 as our pH. All right, let's work on this one here. I'm going to leave some of this information up here. All right. So, a couple of years ago, I don't know how long it was, maybe a year or 2 ago, there was that some trend, people putting Tide Pods in their mouth, ridiculous, right? My thought is, if you want people putting them in their mouths, don't make them look like candy, right? But here is the concentration of a Tide Pod. But before we get into the work here, let's kind of look at the problem a little bit. Sodium hydroxide, is that an acid or is that a base? Base. So we're working with, so here, when it says 3.6 times 10 to the minus 5 molar sodium hydroxide, we know that this is a base. And what does this capital M represent?
Molarity.
Molarity. And molarity is a type of, rhymes with concentration. Concentration, perfect. This represents concentration. So 3.6 times 10 to the minus 5 molar sodium hydroxide, 3.6 times 10 to the minus 5 is our base concentration. Right. If it had been 3.6 times 10 to the minus 5 hydrochloric acid, then we would write 3.65 times 10 to the minus 5 acid concentration, because we can identify acids and bases pretty easily. So here, this will get us started here. So now we know what that base concentration is. So can we put it directly into our problem here? No. So we have to do some work. We have to go back to this over here, and we're going to say our Kw, which is 1.0 times 10 to the minus 14 divided by 3.6 times 10 to the minus 5 is equal to our acid concentration. Zero times 10 to the negative 14 divided by 3.6 times 10 to the negative 5. I have an answer, but I want Azalea to give me the answer to make sure that she's able to work through that.
So,
And we're going to stick with two significant figures here.
okay, 2.78,
Two significant figures, so 2.8
or 2.8, multiplied by 10 to the negative 10.
times 10 to the minus 10. All right. So now that we have this concentration, well, now we can use that value over here. So we have 2.8 times 10 to the minus 10. So we're going to do pH is equal to negative log of 2.8 times 10 to the minus 10. I'm still learning names here. Milex? Oh, okay, got it. Milex. So Milex, what is the pH here? Yeah, let me calculate that as well. Negative log 2.8 times 10 to the negative 10.
9.55.
So this is equal to 9.55. Right? 9.55. Right? And we take a look at our pH scale, right? I mean, it's up there, right? Right up with detergent where it should be, okay? So kind of pretty basic. It's going to do some damage. Anybody tries to, I'm not suggesting it, right? That's my disclaimer. Please don't do this. All right. So we have a couple definitions now. We know how to name binary acids and oxyacids. We can make some calculations with pH. Whether it's an acid or base, we're still able to calculate the pH. Now comes our second definition. Right? So now we have an added definition when we're trying to identify acids and bases. So Bronsted and Lowry have another definition to help us identify acids and bases. So rather than considering hydrogen and hydroxide, they're just focused solely on the hydrogen proton, right? That's what their focus is. We looked at this one earlier. And we really couldn't identify, well, there's no hydroxide, there's no base here. I can't really tell using Arrhenius' definition if it's an acid or base. But we can use it, identify it using the Bronsted-Lowry acid and base rules here. So it will always produce some hydrogen ion. Right? That's all they're focused on. They're just focused on the hydrogen ion. So in an acid-base reaction, we're always going to be producing some hydrogen ion there. An acid is a proton acceptor, and a base, is a proton donor, and a base is that hydrogen proton acceptor. And maybe we shouldn't add, let's add, let me get one from the text over here. I think I have a better image here. Yeah, instead of me drawing it out. So acids, again, acids are going to donate hydrogen, and bases are going to accept that hydrogen. So there's going to be a transfer of a hydrogen from one substance to another substance. So I know that this is a base because we listed it and we identified it as a base. We just didn't know why because it didn't have hydroxide in there. But knowing that this is a base, bases are hydrogen proton acceptors. Which means if we mix this with water, water's not an acid, but water can act like an acid and donate a hydrogen proton. Right. It can donate a hydrogen proton. Now let me draw this out. If we add water to this, this is our base, and water is going to act as our acid. Again, water's not an acid, but it can act as an acid, and it's going to take this particular hydrogen here, will leave, but the two electrons that are here, they remain with it. Right? It's only leaving by itself. Just this proton is leaving. And it just so happens that there's a lone pair of electrons here that aren't paired. So this hydrogen proton can make a bond here. And because it's leaving these negatively charged electrons, is that here we get NH4 plus. It's carrying this positive charge here. So when it accepts it, it's also taking that positive charge. And because these electrons are left behind, we can now see that it produces hydroxide, which lines up with Arrhenius' definition of producing hydroxide. We just can't initially see it, so we need a second definition. So it's not that Arrhenius was wrong, it's just we just needed something more complete in order to help us understand why ammonia is a base, right? So it accepts that hydrogen proton, we get that charge, we get this negative charge here, and now we'll start looking at different substances here. Hydrochloric acid, right? It's not necessarily producing H plus in this reaction that we're showing, but it is producing H3O plus. When we put this into water and ionize it, this is acting as an acid, but water, in this example here, water is acting as an acid. Water is not a base, but it can act as a base. HCl, if I name it, this is hydrochloric acid. I've identified my acid. And I know with Bronsted and Laurie that definition is acids donate hydrogen protons. So this hydrogen proton here is going to get added to the water and we get H3O plus. We bring over that positive charge. Because the electrons here, these two electrons are left with it, is we get chloride ion with this negative charge. With that negative charge. So here, let's see. This type, so water, when we look at water, right? When a substance, not just water, water's not the only substance that can do this, is that when we have a substance that can act as both an acid and a base, we consider that to be amphoteric, right? So it does have a definition there, is that those compounds, when they can act as an acid and act as a base, those are amphoteric substances. And now I think we can finally understand why that H plus, the hydrogen proton, and H3O plus, hydronium ion, why those two are interchangeable when we're talking about acids and bases. And it generally just comes down to simplicity. Is that when we want to ionize something, what do? We put it in what? Water. If I want to ionize base, put it in water, ionize. If I want to ionize an acid, I put it in water, it ionizes, right? So we just simply put something into water to ionize it. Which technically means I can put water and add it to what? To ionize it. I can put it in some more water. So I can take water and add water and ionize it. If this is my acid, then that means this water molecule is going to act as my base. Acids, do they donate or accept hydrogens? They donate. So we're going to take one of these hydrogens here, and we're going to donate it to this one acting as a base. So then we get OH minus and H3O plus. But the reaction seems kind of silly. Right? So what we do say is, to simplify things, we say that water self-ionizes. So water self-ionizes. And if water self-ionizes, we get this simplified reaction. So this is why these here, when we're talking about acid-base reactions, is that they're just interchangeable, right? They mean this. They represent the same thing when we're talking about acids and bases and these reactions here, right? We call it the self-ionization of water. Okay, so let's go back here. Let's go back to these two reactions. We're going to learn some more terms here. The other term that we're going to learn is that acids and bases. Acids and bases contain conjugate pairs. So we can have a conjugate acid, or we can have a conjugate base. Right? These are what we're going to consider to be conjugate acid and base pairs. And we'll just kind of backtrack a little bit to look at these reactions. If this is my base and this is my acid, let's take a look at this one first. Water is acting as an acid. So if water is acting as an acid, after the reaction, it turned into a base. So if this is my acid, this is its conjugate base. If this is a base, after the reaction, this is its conjugate acid. Right? And that always happens after the reaction. Some acid will have a conjugate base, some base will have a conjugate acid. We can look at this reaction here. If this is my acid, this is its conjugate base. If this is my base, this is its conjugate acid. So we can take a look at plenty of acids and their conjugate bases. When we go from acid to conjugate base, it's the removal of one single hydrogen proton. Not 5, we're not moving 3, we're not moving 2, we're just removing 1. And we can see them in all of these examples. This is my acid. I know that acids donate hydrogens, so its conjugate base is going to have 1 less. And we get NH3. And notice the charge go from positive to 0. Here, this is water. If this is my acid and acids donate hydrogens, it's going to have 1 less and we get hydroxide. And notice the charge, we go from 0 to negative. Positive to neutral. Negative to more negative, right? -1 or 1 minus to 2 minus. So each time we remove a hydrogen, we have to adjust that charge. So let's identify some conjugate acids and bases. If this is our acid, and how do I know, one, how can I tell that this is my acid? The hydrogen's out front, right? Dead giveaway. Hydrogen out front has to be my acid. The name of this, phosphoric acid, because this is phosphate. So phosphoric acid. Now, for us to get a conjugate base, acids donate one single hydrogen proton, and then we'll get its conjugate base. This right now is neutral. And what happens when we go from neutral to its conjugate base, we have to adjust the charge. So first, what's the formula going to be for its conjugate base? Andrew, what's the formula for its conjugate base here? How many hydrogens are we going to remove?
One.
One. So what's the new formula going to be then?
H2.
H2
PO4.
PO4. And we're going to go from this neutral charge to what? Then you take a look up there. If you look at water, look at that example. What would the charge then be for this here? Water's the HOH.
HOH.
Yeah.
Minus.
So minus, right? We removed one hydrogen, and then we get this one minus charge. Right? Acid, and this is its conjugate base. As long as there's hydrogens there, as long as there's a hydrogen out front, this can act as an acid. This is amphoteric. H2PO4. This is not amphoteric, but this is amphoteric. If I turn this, and now I say, okay, well, this is now my acid. And I want its conjugate base. Brian, what would the new formula be for the conjugate base? How many hydrogens are we removing? So what would the new formula be? And we have to adjust the charge. We're going to go from 1 minus to, and we have our conjugate base. This is still amphoteric. I still got more hydrogens out front. If I take that, Gabriella, acids, do they donate or do they accept hydrogens? They donate. How many is this going to donate? 1. So if this donates 1 hydrogen, what's our new formula over here? And what's the charge going to be? And we simply just get phosphate now. Right? So we can continue to do. Let's do one more. Let's just do acetic acid. Oh, not O4. What am I thinking? This is our acid, and I want its conjugate base. So do acids donate or do they accept hydrogen? They donate. So how many is it going to donate? So what's the new formula over here for the conjugate base?
C2.
There we go. Yes, so it's going to be C2.
H3.
And we're going to go from this neutral charge up here to what? So we go from acetic acid to acetate. And this is true going from base to its conjugate acid. So we can actually reverse all of this. I don't think we'll go through the whole thing. Let's get some new examples here. This is our base. We're going to want a conjugate acid. And let's do if this is my base, and bases are hydrogen acceptors, how many hydrogens am I going to add to this? Angela, how many hydrogens am I going to add to this? This is a base, and bases are hydrogen acceptors. How many hydrogens am I going to add to this? One. Perfect. Perfect. So this, if I add one hydrogen to this, what's the new formula for my conjugate acid? We just said we're going to add hydrogen. So let's start there. What are we going to get? H. Are we adding oxygen? No. What are we adding? Hydrogen. We just did that.
So 3.
4. So this doesn't change at all. All we're doing is we're just simply adding hydrogens to it. So we get our conjugate base, but this time, before we do the charge, Angela, let's take a look here. Base to its conjugate acid, we're adding one hydrogen, and we're increasing the charge now. Not decreasing, but increasing. Here we have hydroxide to water, we're going from negative to positive, right? Water to hydronium, we're going neutral to positive charge. We're going to have carbonate, right? And we're increasing that positive charge. So by adding this hydrogen, this is what we're adding. We're adding H+. So we're going to go from 2 minus, Angelo, to what?
0. But this actually negative, correct?
Yeah, just negative, right? Absolutely, just negative. So here we get our conjugate acid. Let's use this amphoteric substance. If we're going to add a hydrogen proton to it, what's that new formula? So what's our name? What is that? Anna. Anna. All right. Anna, what's the new formula? And we go from 1 minus to just neutral. Right? So we have our bases going to our conjugate acids. Now, we talked about, you know what, let me see if we need to take a break here. Yeah, you know what, let's take a, before we get into this next part, let's take a little break. And then we'll start talking about the next portion here. All right, so let's take at least 15 minutes. Let's come back at, let's say 9:45-ish, 9:50, right around there. Let's, yeah. Somewhere in between. All right. So let's continue here. All right. So, talking about the pH scale and these substances, we know that substances can be kind of acidic or very acidic, kind of basic or very basic. So, we can have strong acids and weak acids, right? Weak acids being kind of acidic, strong acids being very acidic, right? So, strong acids, note the direction of that reaction arrow, right? It is not a reversible reaction. So here, let's go with HBr. So HBr is a strong acid. We ionize it. We're going to get go plus, we're going to get Br minus, right? So that's not to say for a weak acid. Let me identify a weak acid. So this is a weak acid. So this is acetic acid. If we put acetic acid into water, weak acids are reversible. So weak acids will get some acetate, plus we'll get some hydronium. This is my acid, this is my conjugate base. If this is acting as my base, this is our conjugate acid. This is my acid, this is our conjugate base, right? But strong acids ionize completely when we put it in water. So if I were to take this strong acid, here's a beaker of water. I'm going to take hydrochloric acid. This is already water in here, and we are going to completely break this apart. So 100% of this. So all of this will produce these ions. So at the end of the reaction, is any of this left? No, it's all been used up, and all of it has been used to produce this. Weak acids are different. Weak acids only partially ionize, they slightly ionize. That if I stick this in water, let's see about, I can't remember the exact value. Might be less than this actually. So about 3% of that will ionize. So we still have quite a bit left. So in the beaker, if I were to put this into a beaker, is that we would still have acetate and acetic acid in that solution. So strong acids ionize completely, weak acids only partially ionize. And the same thing happens for strong bases and weak bases, right? Strong bases, same thing, it's going to completely ionize. It's not going to revert back to, right? So if we take this and we take this and put this into a reaction together, it's not going to reverse up. We're not going to make hydrobromic acid, right? So this is just a one-way street. But here, this can be pushed back and forth. And again, same thing for strong bases, weak bases. Strong bases, weak bases. We put a weak base into water, it's going to just slightly ionize. We put a strong base into water, and it's going to completely ionize. So I think this is probably a better image to explain that, right? Is that here we put hydrochloric acid, strong acid, and all of it is going to ionize. When we put a weak acid into the solution, is that it just kind of partially, slightly ionizes. So how are we going to know, one, which reaction arrow are we going to use? If I were to provide you with, let's say, hydrofluoric acid. If we put this into water, are we going to use this reversible reaction, or are we just going to use this reaction here? So we have to identify it. Well, is it a strong acid or is it a weak acid? And we have a bunch of calculations that we can make now, right? We can make a calculation, get the pH of it, and we can kind of identify whether that's going to be a strong or weak acid. We could go that route. But a much easier way is that we're just going to memorize the 6 strong acids. So these are your 6 strong acids: hydrochloric acid, nitric acid, sulfuric acid, right? But we're going to memorize these strong acids. And if it's not one of those acids, then it's a weak acid. So, Azalea, is this a strong acid or a weak acid? How do you know? Because it's not one of the 6, right? It's very easy, right? So we just memorize the 6 strong acids, and if it's not one of those acids, it will simply just be a weak acid, right? That's how I know that this is a weak acid, because it's not one of the strong 6 acids. So what reaction arrow would I use, right? Simply because it's a weak acid. So that also pertains to bases. So for this class, these are going to be the strong bases that we're going to worry about, right? Sodium hydroxide, potassium hydroxide, calcium hydroxide. It's not one of these strong bases, then it is a weak base. So here, is this a strong base or a weak base? It's a weak base because it's not one of the strong 3 bases, right? So we can identify strong bases, weak bases, strong acids, and weak acids. Because we're on this topic of weak acids and strong acids, I'm gonna jump into a different section, and yeah, I think it's probably better we jump into this section instead of coming back to it, since we're already talking about weak acids, strong acids. Is that weak acids make what we call buffers. Weak acids will make what we call a buffer. So a buffer, right? A buffer is a solution that will resist changes in pH. And physiologically, we have a bunch of buffers. Saliva, stomach acid, right? Those are all buffers, right? That will help our bodies resist change in pH. Right? I can drink lemon juice. Is it very sour? Yeah. Is it going to destroy my insides? No, because we have what's called a buffer. Right? And again, it's going to resist change in pH. If I add a little bit of acid into this solution, this buffer's job is to resist any change in pH. So even if I put a little bit of acid in here, the pH shouldn't change. We talked about making something more acidic, more basic. If I want something more acidic, I add more acid. If I want something more basic, then we have more base concentration, right? So here, even if I add a little bit of base, the pH should not change. If I put a little bit of acid, the pH should not change. And at the very beginning of lecture, I also introduced this idea that acids neutralize bases and bases neutralize acids. This is my acid. Then this over here is its conjugate base. And we see that this is a reversible reaction. So if I were to add a little bit of acid to this, acids neutralize bases, bases neutralize acids. If I add base to this, If I add base to this, is there an acid available that will neutralize this base? If I put this in, I'm going to put some base in here. I'm going to put it in the solution. Is there an acid that would neutralize this? Yeah, it's right here. So this will neutralize this base. If I decide to put acid in here, is there a base available to neutralize the acid? It's right here. Right? Because this is a reversible reaction. So I do have a base that would neutralize the acid. So if I'm neutralizing the acid, if I put acid in here, this is my base. Melissa, does bases accept hydrogens or do they donate hydrogens? They accept hydrogens. So if I put some acid in here and bases accept that proton, this is going to get neutralized by the base, and it's going to make what? If I put this and this together, what is it going to make? It's going to make more of this. Right? So we neutralize the acid and it makes more weak acid. Okay? So if I add acid, it makes a little bit more of this weak acid. If I add base, I'm going to make a little bit more base, because this is a hydrogen proton acceptor. So it's going to take this hydrogen and we're going to make more base. So kind of a general, if I add base, we're going to make a little bit more base. If I add acid, we're going to make a little bit more weak acid. But we can identify acids and base. So this reaction here is really important, right? Weak acids make buffers. Weak acids make buffers. Right? Let me repeat that again. Why would I repeat such information again? Weak acids make buffers. Let's use a strong acid. If I put this into water, all of this gets ionized, right? And this is our acid. This is our conjugate base. But remember, this is not going to go this direct. This is not a reversible reaction. So if this is an acid, this is my base. If I put a base in here, is there an acid that would neutralize this? No, it's gone. If I put an acid in here, technically we have a base, but can the reaction go backwards? No. So strong acids don't make buffers. Right? We need a weak acid. Water can act as a base. Water can act as an acid, but water's not an acid. Right? Water's not a weak acid. So weak acids make buffers. Let's go with a practice problem here. We're going to write some reactions using this concept, and let's get a different weak acid. So phosphoric acid is a weak acid. Let's go with its reversible reaction here. All right, weak acid. If this is my weak acid, what's my conjugate base? Somebody tell me my conjugate base here. We're donating one hydrogen. What's our new formula? H2 PO4 minus plus H3O plus, right? So this is my weak acid, and this is our conjugate base. If I were to add, I'm going to leave this one over here. If we add base into this reaction, I want to write a new reaction. If we add base into this buffer, I want to know what the new reaction is. So if this is base, it's going to get neutralized by what? The acid, right? Bases neutralize acids, acids neutralize bases. So this acid here is going to neutralize this base. Proton donor, proton acceptor. Plus water. This weak acid neutralized this base. So if we add base, we're going to produce more base, because this is our conjugate base. But in every neutralization reaction, water is always going to be a product. We're going to have some conjugate base plus water, some conjugate acid, right? But here, anytime we neutralize this acid here, neutralization reaction, the neutralization reaction will always produce water. So if we add base, this is the reaction here. If we add acid, if we were to add acid into this reaction, what's going to neutralize this acid? It's conjugate base. So this acid is going to get neutralized by this base, acid base, proton donor, proton acceptor. And again, neutralization reactions will always produce water. So here, acid, base, we have our conjugate acid, and water's hydronium's conjugate base here, right? But these reactions are reversible, right? But we do need to have a weak acid for those, right? But those are neutralization reactions. So a neutralization reaction will always produce water. So we're going to have some salt and right here some water. Now, neutralization reactions. All right. So neutralization reaction. So let's take a look at this neutralization reaction here. Here, this is HCl plus sodium hydroxide. Let's use sulfuric acid plus some potassium hydroxide. Strong acid. strong acid. So I'm using this reaction arrow here. Right? Neutralization reaction. This neutralization reaction here will form salt and water. But these are what we call double replacement reactions, and we learned those in Unit 4. Double replacement reactions. Right? Remember our double replacement reaction. AB plus CD, and we're going to get AD plus CB. A, B, C, D. Double replacement reaction. This is going to go with this. This is going to go with this. This is going to go. This will go. One of the hydrogens will go with there, and then this is going to go here. But double replacement reaction is that we're going to get salt plus some water. Is we're going to get salt. Okay. There we go. I needed to balance the reaction real quick. All right. But double replacement reaction when we're looking at neutralization reactions, right? We're always going to produce salt and water. They form from a natural neutralization reaction. So using that principle, that theory for neutralization reactions, this is the experiment we're doing in today's lab. Right? Is we're going to do something we call a titration. Now, this titration is going to involve some stoichiometry in the calculations, but we perform these to determine unknown concentrations. We did an unknown concentration the other day. Right? We made some calibration curve. We used the spectrophotometers to get some absorbance, made some curve, and we were able to guess some concentration. So this is another method to determine unknown concentrations, and we use the principle that acids neutralize bases, bases neutralize acids. Right? So in today's lab, this, inside the burette, is going to be some sodium hydroxide, the base. And in your flask is going to be some vinegar. And if you don't already know, vinegar is about 95% water, 5% acetic acid. Okay? But in here, we're going to have vinegar. We need to know the concentration of the acetic acid that's in this vinegar. Right? So we're going to put base in there, the sodium hydroxide, until it neutralizes. Once it's neutralized, right, you see this light pink swirl? This is going to happen each time you put a drop of base into that vinegar. You're going to see this little pink swirl, and then it'll disappear. As fast as it appears, it's going to disappear until eventually the entire thing turns pink. Now, there is another chemical in here that makes it turn pink. When you put sodium hydroxide and vinegar together, acetic acid together, it doesn't naturally turn pink. We put in something called phenolphthalein. And once that phenolphthalein reaches a certain pH, it will change color. So we're going to see this pink color here. But we need to get to this point where it's neutralized, because that's what we consider the equivalence point, right? Where the moles of acid is equal to the moles of our base. The moles of acid is equal to the moles of base. And we've done these reactions, and we've done stoichiometry in Unit 4. We did some stoichiometry and we converted moles of one thing into moles of another thing. Right? We use the chemical formula, or the balanced reaction. We use the balanced reaction. We use the coefficients in that balanced reaction to convert moles of one thing into another thing. And that's the stoichiometry that we're going to be doing today. So let's do a practice calculation. This isn't going to be the identical calculation. This calculation is similar to what we're going to see in the homework. So you do have homework for this unit, and this particular example will help you understand the calculation in the homework. It'll help you understand the calculation on the exam. Okay? So calculate the molarity of sulfuric acid. So there's our reaction here. So sulfuric acid, we're going to add 2 moles of sodium hydroxide. We're going to get some salt and water, our sodium sulfate, and we're going to get some water there. And we have some information here. I'm first just going to initially write this information down. So sulfuric acid, we have H2SO4. There are 10.00 milliliters, right? And this is the volume of sulfuric acid. Volume of our base, sodium hydroxide. Volume of sodium hydroxide, 16.50 milliliters. Let me rewrite this a little bit. We have the concentration of our base, and that is 0.1820 molar. And what we're trying to identify is the concentration of this unknown acid. So step 1 here is we need to go from, well, not step 1, this is the direction we're going here. We need to go from moles of sodium hydroxide to moles of sulfuric acid. All right? Moles of sodium hydroxide to moles of sulfuric acid. So in stoichiometry, we can't use this capital M. Right? Moles stands for molarity, and what are the units of molarity, Zuri? Grams over milliliters would be concentration for, that would be for this here. That's the percent MV. That's our grams per milliliter. Molarity. Stay with me. You got to just keep throwing stuff out. Molarity. Let's spell this out. I'm going to spell it a great way for you to know this. Is what?
Moles.
Over.
Liters.
Yes, perfect. How did you decipher that? All right. So molarity is moles over liters. So in order to go from moles of sodium hydroxide to moles of sulfuric acid, well, we have to get rid of, let's write this here, right? If molarity is equal to moles over liters, we have to get rid of this. We can't do this portion here until we remove the liters here. So that would be step 1. So here's our concentration of base. 0.1820 moles of base over liters of base. Units are really important, right? Because this is milliliters. This is volume of acid, and this is volume of base. So I'll go back to the image here real quick, because I want to make sure that we're clear where these two volumes are, what they represent. So in this titration that we're doing, there was 10 milliliters of some unknown acid, sulfuric acid. So this is our, in here in the flask is the 10 milliliters of sulfuric acid. And in order to neutralize this 10 milliliters of sulfuric acid, it took 16.50 milliliters of this base at this concentration to neutralize this unknown concentration of acid. So that's what these volumes represent. So in here, in the burette, we dumped out 16.50 milliliters of base in order to neutralize the 10 milliliters of acid that were in the flask. So we have liters of base. Well, this is milliliters of acid. This is volume. Here's my volume of base. So let's convert this real quick. We're going to say for every liter, there are 1,000 milliliters. Then we can say we have 16.50 milliliters of base. So this unit goes away, this unit goes away, this unit goes away, and this unit goes away. And now we have moles of sodium hydroxide. So now that we have just moles of sodium hydroxide, we can now use the balanced reaction to get our mole ratio. The ratio of moles between moles of sodium hydroxide and moles of acid. So in this reaction, there are 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. This comes from the balanced reaction. There's nowhere else to get this except for the balanced reaction. So we're going to use that information, and we're going to say for every 2 moles of sodium hydroxide, there's 1 mole of sulfuric acid. There's our mole ratio. So now we've converted moles of one thing into moles of something else. Because this unit here will cancel this unit here. And now we have moles. But this is what we're trying to get. I still don't know what the concentration of this acid is yet. But if I want the concentration, I know I need to have moles over liters. And I do have a volume down here. I have volume underneath. So, the unit right now, these milliliters, when we're thinking about this, it's moles, some amount of moles over some amount of volume. Moles over some amount of volume. Moles over some amount of volume. We can take care of the milliliters and convert it to liters. That's not an issue. But we need to put it in the denominator because that's where the volume belongs. The volume belongs in the denominator. It's moles over volume, moles over liters, moles over volume. And then the last part here, well, now let's convert that. So for every 1,000 milliliters, there is 1 liter. And those units cancel out. To make our calculation even a little bit, just a little bit easier, this 1,000 here will cancel out this 1,000 over here. So now we can calculate this. It's up to you how you want to calculate it. One way to calculate it is take this times this and put it up here. Take this times this and put it down here. Then take this and divide it by this and then get some final answer. And that's perfectly fine. Generally, you will not see me do that. I don't multiply and divide by 1. I multiply everything in the denominator. I only like to hit equal one time, if I can. Right? If I can help it, I will try my best to hit equals one time. The more times I hit equals, the higher chance I get to make an error. So I multiply everything in the top, divide everything in the bottom, and then I hit enter, and that's what I'm going to do here. As I do this, I'm going to put 0.1820 times 16.5. Denominator, divide by 2. Denominator, divide by 10. And I get a concentration. So I can pick somebody, or somebody can just say, hey, this is what the answer is. What do we got for an answer? And we'll go with 4 significant figures.
0.1502.
0.502 what? Molarity. So molarity of chocolate chip cookies.
No,
Orange juice.
the H2SO.
Yes, there we go. That's a perfect answer. Use the same method on the homework. Right? This comes directly from the homework, that there's other values that you're going to use, but the steps are going to be the same. Right? The steps are the same in calculating it. In today's experiment, there's some guidance in order to do this. I think it's probably a little more complicated in the lab because we're using, we have to get some amount in grams and convert that. But here we've been able to answer that question, right? I don't think it's necessary to calculate the percent MV here. And we did finish and already talk about buffers. So that ends Unit 6. We have an exam on Tuesday. Now, here's the sad part. We've just completed general chemistry. Next week, we start organic chemistry. And with organic chemistry, 99% of the calculations go away. I know, you don't cry. If you cry, I'll cry. We don't want that to happen, right? Organic chemistry is much different. I would say out of all 4 exams, I would say that exam 2 is probably the most difficult because of Unit 4. Unit 4 is huge, right? Unit 5, Unit 6, probably a little easier to understand as long as we were able to grasp Unit 4. But, memorize what I tell you to memorize. Know those definitions. Don't spend 90% of your time trying to learn all of the calculations, right? There's 13 calculations on the exam, I think, right around there, right? So there's another 27 questions that come from concepts and definitions, right? Concepts of isotonic, hypertonic, hypotonic solutions, oxidation questions, nomenclature, how to name acids, how to name oxyacids. So there's different concepts that we have to deal with on the next exam. Balancing equations. I've had students spend a weekend trying to balance reactions. There's one balancing equation on the exam, and it's multiple choice, right? So don't devote all your time trying to balance equations. The balancing equations comes over time, right? The more you balance, the better you get at it, right? But I wouldn't spend an exorbitant amount of time trying to balance equations when, again, there's one and it's multiple choice on top of that, right? So you should be able to decipher, just how to balance that reaction, right? As long as you get the concept of balancing, you should be able to balance that equation, right? So just kind of put a fair amount of studying into both concepts and definitions, right? Concepts, right? Oxidation is a concept. Naming acids, right? Those are concepts that we learn, okay? And then, of course, some definitions along with these calculations that we've seen. So hopefully you guys get a good jump on that. The videos will all be up 4, 5, and 6 if anybody needs to review those.